Also, if you feel like any question is left out and you want to ask the question after the class, we can also do that. But meanwhile,
Yes,
as well, if you have any question, you can ask that.
right, ma'am. Although I told them earlier also, it seems that they have not posted any questions. So, ma'am, we can move forward and we'll also post it in the WhatsApp group to post the questions towards the end or in the middle as you wish.
Yes, 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 yes.
Okay,
No
ma'am.
issue.
So let's jump into the session today. Over to
Okay,
you, ma'am.
okay. Thank you, sir. Yes. Pardon my voice, and it's again a little more broken, kind of. But today is formally the end section or end session for the introduction to quantum computing and technology. So we will be starting with that, and also let me start with what we covered in the last class. So, or where actually we are supposed to start with. So we covered a little of the quantum theory and most importantly the Schrodinger equation. So this is what we covered, Schrodinger equation primarily, and followed by that we entered into a detail of the Dirac notation, understanding of that. Okay, with respect to the single qubit as well as multi-qubit gates, a multi-qubit quantum gates and quantum states. So this is all that we have done yesterday, a detailed version of these two. And the last one was we also have started with the quantum gates. So which was kind of a preliminary concepts that you should be having if you have to understand the quantum circuit as well as the a few leftover topics of quantum mechanical postulates, which is quantum teleportation as well as the super dense coding. So these two are the topics that are left over. So today we will start with, and I also had mentioned in details the Hadamard, the Pauli XYZ matrices, all three of them, as well as the C naught, and a little of the C square naught or Toffoli, as well as a swap gate, and the general R theta gate. Okay, so all these gates we already covered at least in an initial way for the introductory classes so that we understand these theories as well, which we are going to cover today. So today we will start with initially a concept that is called a Bell state creation. We will start with that. So it's part of the entanglement itself. Now, once we have a detailed understanding of the Bell states or what are the four Bell states available, then we will enter into the quantum teleportation theorem and we will understand that why, without even no cloning or without even cloning of a quantum state being supported by the receiver's end as well as the sender's end, we can actually transfer some message from sender to receiver. So this is the first point. Second point being the quantum super dense coding. Super dense coding. And once you have that understanding, we will try also to analyze a little bit of what is available in Qiskit. So we will try to see some of the that transpiler or composer environment. Though I am pretty sure that in next session you will be having a detailed understanding of this thing, and there will be a detailed session on how you can create your own Qiskit key with which we can access your session, how you can create your own quantum circuit and all those stuffs. So right now for QT02 we will just, if some time permits, we will look into some of the features available over there. We'll see how the drag and drop works and how the probability density function or PDF that actually differs with respect to several gates that we have seen. And followed by that, what is our last target for today is we will try to look into the some of the quantum error correcting code. So I have introduced this thing because since for decoherence we don't have any as such theory available, but for the quantum mechanical postulate at least we can have some understanding of how the error correction of those erroneous qubits which are available right now that can work. Okay, so for that I have introduced these quantum error correcting codes as well. So if time permits, so this is how we are going to proceed. So this is 1, this is 2, 3, 4 and 5, and in this particular order we are going to continue as per the requirement of the syllabus that we have, as well as the demand for exactly if we have to like comply by the syllabus of the QT02, we actually should be following these 5 steps, right? Okay. Let me hide the screen. I hope my screen is visible and I'm completely audible. Otherwise, please interfere in between so that nothing is left out. So now we will start with the first thing, that was the Bell state creation. So Bell state is nothing but kind of a first step in entanglement, and we also have mentioned that there is a Hadamard followed by a CNOT combination that you can follow in Bell state creation during Bell state creation. So what it is kind of like 0, 0 plus 1, 1 divided by root over of 2, right? Where this is qubit 1 or the first qubit. Similarly, this is qubit 1 and this is qubit 2 and this one is qubit 2. So from these things, configuration, you can understand two things. Like first thing is there exist two qubits as inputs. And the second is like on those two qubits, so that means qubits are shared in order to establish the entanglement between two parties. So how physically we can represent, and this is an arbitrary quantum state represented by the symbol ket psi. So how we can implement this state is, say for example, so that means there are two qubits, say q0 and q1. These are the two qubits. And initially they are initialized with, if nothing is specified, then that means they are initialized with the ket 0. That is, they are initialized with the column vector 1 and 0. This thing. Now we will be applying an Hadamard gate on q0, not on q1, and then we will be applying a C0 gate where, so this is a Hadamard gate and this one is the C0 gate where q0 acts as a control, and this also it represents a C0 gate where q1 behaves as a target. And on both of these you are doing a measurement. This is the measurement gate symbol. Now if you do that, let me assume the time evolution of the quantum states as whatever we have learned in the Schrodinger equation on how from the initial state say q0 till the final state qt, how the Schrodinger equation or the Hamiltonian operator that works. If we have to consider that, so there are two initially, so the initial configuration is two qubits, a tensor product being applied on both of the qubits. Then we are applying the Hadamard on the first qubit. So this will make it ket 0 plus ket 1 by root 2 product. The second qubit is as it is, as there is no such operation on that. So it will be as it is. So now if I have want to write it, it will look like, say, 0 0 plus 1 0 whole divided by root over of 2. Right? Now what we are applying is, we are applying, the next step is we are applying a C naught gate, where Q0 is a control and Q1 is the target. Now if we apply this thing, this means this is Q0, this is Q1, this is Q0, and this is Q1. Remember the qubit number 1, qubit number 1 is the first one, and similarly the second one are qubit 2 and qubit 2. Now, if we apply a C naught or a control NOT gate where Q0 is the control and Q1 is the target, then the resultant state will look like, see, 0 is control. If control is 0, then we shouldn't be doing anything to the target. From where we are getting this theory? From the truth table of C naught gate, which we have learned yesterday. So if control is 0, we shouldn't be doing anything to the target. Plus, if control is 1, if it is a C naught, that means we just need to flip the target qubit. Flipping means if it is 0, then it will be 1. If it is 1, then it will be 0. So that means this 0 will now become 1. So this is the resultant state of the first kind of entanglement theory, where we believe that if qubit 1 is in state 0, then qubit 2 will also behave in a form that it is in state 0, and vice versa. If it is like in one state, then q1 will also be in one state. And this is the fundamental theory for Bell state as well as entanglement. So entanglement is one of the postulates which can be realized using the help of the Bell states. Bell state means this is one of the Bell states that we have created, which is ket 0 0 plus 1 1 divided by root over of 2. Okay. Now once you have understood this thing, and you have a clear understanding, because see why we actually have posted or postponed this entanglement and the teleportation discussion to the last class is so that we have a detailed understanding of what is the Hadamard, what is CNOT, how it operates, and all these things, right? So what are other Bell states possible? So Bell states possible can be like 0 0 plus 1 1 by root 2, then it can be 0 0 minus 1 1 by root 2, then it can be 0 1 minus or plus 1 0 by root 2, and it can be 0 1 minus 1 0 by root over of 2, and all these four states are called Bell's entangled quantum states. And why this is very beneficial? Because this is the fundamental ground for us to start the basic concept of quantum teleportation. Okay, so now on this note, we will enter into quantum teleportation. So from the term itself, you can understand it is sending something from one point to another. So this is the process. This is the process of sending one quantum state. And also just follow, before I start the teleportation and superdense, also follow, if you understand these things, then you will be having a kind of an advantage in quantum algorithm, as well as you will be able to understand the time evolution in a practical sense as well. So please do a lot of focus over here. So from a quantum circuit, from a quantum oracle, how to proceed or how to interpret the quantum gates and quantum operations, if you have to understand that, you have to put a lot of like concentration on these two theories as well. And also in quantum cryptography and communication also, these are the similar things that is going to be repeated. So there also we are going to have some similar flavor of these concepts, right? So quantum teleportation, it is a process of sending one quantum state from one place to another. This means, or that means, say, Alice and Bob are at the two ends of the communicating channel, and Alice has a symbol like alpha ket 0 plus beta ket 1, and this is some arbitrary state, and this is the state that Alice wants to send to Bob. And also, there is another consideration, that is, Alice has no precise information about the state to be sent to Bob. So, this information also is not very clear to Alice. So, that means there is just an arbitrary state that Alice wants to send to Bob without having any information about the state itself. Now, now the catch here is, what is the catch? How to implement quantum teleportation is, when earlier Alice and Bob met, Bob is the receiver, Alice is the sender, for example. So they agreed, or they decided to share 1 qubit each out of the Bell's pair. So that means one will be available to Alice and one will be available to Bob. So the point number 2 is, Alice and Bob will share 1 qubit each of the Bell states which is of the form this. So this is an entangled state. So Alice is starting with state 1, which is alpha 0 plus beta 1, which Alice wants to send. So this is state 1. Second is 0 0 plus 1 1 by root over of 2, where this bit and this particular bit, say bit 2. So Alice has access to bit number 2, and similarly this one as well as this one is bit number 3, which Bob has an access. Okay, so on that note, we will start with first having the quantum circuit for teleportation. So which looks like this. Say 1 is alpha 0 plus beta 1, and that is actually going through some Hadamard followed by some measurement. Second qubit, qubit number 2 and qubit number 3, which is part of the entangled pair, is here, where this one is making this control knot. So this is a C0 gate. And this is another measurement. and third one will go till this part, and based on this outcome it will first enter into a Pauli X gate as per the outcome, then it will go to a Pauli Z gate, and post that we will be receiving the quantum state gate psi, which is initially the alpha 0 and beta 1. So we are supposed to get this alpha 0 and beta 1. Okay, and this part is a part of this part is a part of Alice's encoding and measurement. And rest is a part of the classical channel. Okay, so therefore, if we apply a Hadamard on first qubit and a measurement on both first and second qubit, which is a part of Alice's to do, we are going to get alpha by root over of 2 into gate 0, then 0 0 plus 1 1. Through some algebraic simplification, we can get this thing plus beta by root 2 times gate 1 into 0 0 plus 1 1. Now, if we separately extract out, if you see here, entacle pair are shared by Alice and Bob. This is something that Alice have. So if we separate out or extract out what Alice only has, that is the first and the second qubit, and we will keep the third qubit as it is, then it will look something like, say, this thing. So now, separately extracting out Alice's part, which is the first and second qubit, equivalently, we can write as 1 by root 2 alpha 0 0 times 0 plus alpha 0 1 1 plus beta 1 0 0 plus beta 1 1 1, where of course this is control, this is target. Similarly, this is the control and this is the target. Similarly, this is control, this is target, and this is control and this is target. Now what Alice is doing, Alice is applying his own C naught. Now on Alice's C naught, it will be like 1 by root 2. Control is 0, so no operation. Again control is 0, so no operation. Plus control is 1, so target will be flipped to 1. Okay, plus beta, control is 1, so target will be flipped to 0. So this, if we write them together, it will be alpha 000 plus alpha 011 plus beta 110 plus beta 101. Now, if you also note that Hadamard on Ket 0 makes it like Ket 0 plus Ket 1 by root 2, and similarly, Hadamard on Ket 1 makes it like Ket 0 minus Ket 1 by root 2. So this is equivalent to minus, and this is equivalent to your plus. Now, if we do this on first qubit, like only on the first qubit, then it will something look like say 1 by root 2 alpha. Then ket 0 on Hadamard will be ket 0 plus ket 1 by root 2 times ket 0 plus alpha. Again on ket 0, that will make it this thing ket 1 plus beta. Now this is ket 1, which on Hadamard will be ket 0 minus ket 1 by root 2 times ket 1 into ket 0 plus beta ket 0 minus ket 1 by root over of 2 times ket 0 and ket 1. Now, taking the 1 by root 2 outside, if you do that, and if you extract a 0, 0 together, right? So 0, 0, then it will be alpha 0 plus beta 1 plus if we take out 0, 1 together, then it will be alpha 1 plus beta 0. If it is like 1, 0, then it is alpha 0 minus beta 1, and if it is 1, 1, then it will be alpha 1 minus beta 0. Now whenever Alice makes a measurement, she can get either, because she has access to the first and the second qubit. So this is the first, this is the second, and this entire thing is the third. Similarly here also this is first, so this is second, this entire thing is third, and similarly it happens. Now that means whenever whenever Alice makes a measurement, she can get what? Anything out of the first two qubits. So she can get either 0, 0 or 0, 1 or 1, 0 or 1, 1. From where we are getting it? From this thing. Either this two or this two or this one or this one. Now, depending on what Alice gets, what Alice will do? Alice will use a public channel, which can be like a telephonic channel, to tell Bob that what she got. So now Bob would Bob would remember that this is exactly the 2 bits of classical information that Alice has sent to him. Okay. So now Bob would remember the bits, or say the exactly the 2 bits of classical information which Alice is, or Alice will be sending. So only that information will be available from Alice's end to Bob's, whether it's 00 or it's 01 or it is 10 or it is 11. Now say Alice is telling Bob, Alice is telling Bob that say I got get 00. Now we will be interpreting that what is the meaning of Alice is saying 00. So say Alice now measures this thing and sends this information over a telephonic channel to Bob. That means Bob must have received alpha 0 plus beta 1, that is the third qubit that Bob is supposed to receive. If that is the case, then what is the original state that Alice wanted to send to Bob? It was alpha 0 plus beta 1. And right now, what Bob has? Alpha 0 plus beta 1. So that means Bob shouldn't be doing any operation as he has received the correct set of operation. So, on that note, if that is the case, if Alice is telling Bob that I got a 00, then that implies Bob does not have to do anything as he already received alpha 0 or ket psi to be equivalent to alpha 0 plus beta 1. Now say the second case where Alice has sent 01 to Bob. That means Bob has received alpha 1 plus beta 0. But what Bob is supposed to receive? Alpha 0 plus beta 1. That is, I must be applying an X gate on both of the qubits in order to get the, or both of the pure states in order to get the desired outcome. So that means case 2, and this was case 1. So case 2 is Alice has 01 and it has sent this information to Bob. And what Bob received? It is alpha 1 plus beta 0. Now, this particular state on some quantum operation will make it, if we apply, say, X gate or the NOT gate or the flip gate, then it will make this 1 to 0 and this 0 to 1. So it will make it alpha 0 plus beta 1. Is this the correct set now? Yes. Case number 3 is Alice has received 10. Let us see what was the state. So for 10, it was alpha 0 plus alpha 0 minus beta 1. So that means we don't have to do any phase gate for 0, but definitely one phase gate we have to apply for 1 in order to make the plus 1 to the minus 1. So that means here we have to apply simply a Z gate. So this on Z gate, which is a phase gate, will make the gate 0 as gate 0 itself. Then 1 on Z will make it minus 1. So this is minus of minus beta 1. So this is alpha 0 plus beta 1. So again, this is the original state that Bob also will be receiving. If Bob does for the case number 2, either X gate, or case number 3, the Z gate. Then the fourth case is where Alice has 1 1. Then it is alpha 1 minus beta 0. Yes. So case number 4 is when Alice has 1 1. Then Bob must have received alpha 1 minus beta 0. That means first I have to apply an X gate in order to make it alpha 0 minus beta 1. Then I have to apply a Z gate in order to make it alpha 0 plus beta 1. Right? So these are all the four cases that Bob can receive the qubits details about, and this is how through several quantum gates Bob actually can get the or can construct the original quantum state that Alice wanted to send to Bob. So what we can conclude is at the end what we have achieved is Alice and Bob both have started with the state, say alpha 0 plus beta 1, and Alice and Bob share a Bell pair which is 0 0 plus 1 1 by root 2, and by having certain number of measurements by Alice followed by a classical communication channel which was established between Alice to Bob. All these things imply that Bob is able to get the state or reconstruct the state out of teleportation. Okay, now this is a theory. You can see that without any information being shared directly to Bob, only by sharing some of the classical information from Alice's end to Bob's end. The only constraint is they will be like Alice and Bob both will be sharing a part of the entangled pair, and we can see that ultimately Bob is able to reconstruct the quantum state alpha 0 plus beta 1, though Alice has not sent alpha 0 plus beta 1 directly to Bob. Rather, what Alice does is Alice sent a classical communication message that can be 00 or 01 or 10 or 11 to Bob. Now, on interpreting those messages, Bob actually has recreated a particular arbitrary quantum state. So, which also guarantees that a no cloning theorem holds true, because this is not a cloning, this is reconstructing what we already have. Okay. So the two questions here, what we can have is, we never have said how far is Bob from Alice. Can they be separated by a space-like distance? And if it is so, are we able to transmit a state at a speed which is greater than light? But this is again against the theory of relativity. But if you carefully notice that we have used a classical communication channel where there exists a classical information either 0001, 10 or 11 to be sent from Alice to Bob. That means Alice must be informing to Bob something intermediate, something in between. Then the theory of relativity holds true here itself, meaning nothing is really at a speed which is higher than that of a light. Second question is, so first one is, since we are relying on some classical messages, zero zero, 01, 10 or 11. So that means the theory of relativity holds true for this particular theory as well. Second is there any cloning done in teleportation? So cloning, the answer to this is no, there is no cloning, any cloning, as Bob has simply Bob has simply recreated the quantum state. Okay, so this gives an end to the quantum teleportation theory. So, what are the observation that we have seen here in teleportation is that here basically what we are doing is we are sending some classical information through some classical channel, that can be some bits of information like 000110 and 11 to Bob. And Bob, basically, on receiving those classical bits of information, since Alice and Bob both are sharing some sort of entangled pair, then Bob's part of qubit are being affected because of the application of simple quantum gates. And due to that effect, once Bob has the third qubit available with him, just before he measures, he will be applying a further operation. So where all these operations are defined in a predefined dictionary, that if 00 is received by Bob, then Bob is not supposed to do anything. If 01 is received, then simple 1x get or not get is required. If it is like 10, then simple a z gate or a phase gate is required. If it is like both alpha 1 minus beta 0, then that means we have to apply both the x gate as well as the z gate on the quantum circuit. Okay. So this is the first notion. Let me take a pause here. Let me just take a few questions. I hope a lot of you have joined by now. So anyone who has any question, you can ask me. Otherwise, I will enter into the next part. Alice and Bob qubit, yes. Just remember the first qubit is the original state that we have. Second and third qubit is the entangled bell pair. Now Alice has the first qubit, where he has the or she has the kind of the arbitrary state which Alice wants to send to Bob. That means qubit number one is something on which Alice dedicatedly has some access. Then qubit number two and three, they are part of the entangled bell pair, which also we are sharing between the Alice and Bob. So qubit number 2 is something that we are sharing with Alice, and qubit number 3 is the only one that we are keeping with Bob. So in short, that means qubit number 1 and 2 is a part of what Alice has. Qubit number 3 is something that Bob has. Okay? Okay. Morally, I guess this was the doubt, as well as like Shoujon no. Yes, K Shoujon. I guess this was the doubt. Anything else? We can definitely make it any state. And this is just a representation of an arbitrary state where we have an alpha and beta. We can create any of the quantum states. From ket 0, if we simply apply an Hadamard, then it will be ket 0 plus ket 1 by root over of 2. Right? Now, if we do not want to mention about what is our, say it is an, what is the challenge here? We have to transfer an arbitrary state where we cannot clone that one. So the arbitrary state representation we have represented with the symbol alpha 0 plus beta 1, where alpha and beta are the corresponding probabilistic amplitudes. Then simply what we can have with 1 by root 2, 1 by root 2. So here we have it like alpha and beta. Okay. QC takes input from classical world. Now this is an actually an hybrid architecture where we quantum teleportation is a process where actually we send some classical information in order to send some quantum information in terms of an arbitrary quantum state from sender to receiver. Okay. Just check whoever has just some doubt with the entangled state, just check with the like Bell state that we discussed while creating the receiver side quantum state gets also importance to use it. What are the parameter importance used for creating the phase energy level? I'm not very sure about the phase energy level. What do you mean by this thing? But basically, yes, according to the application, because see, these are all hard coded initially in theory, that If you receive anything like 0 1, then these are the set of operation like application of a Pauli X gate. If you receive 1 0, then this is the application that you have to apply a Z gate. And if it is a 1 1, then you have to apply X gate followed by a Z gate. And if it is 0 0, then it is no operation. So all these things are already hard coded. This is the logic that we already have defined. What I have shown to you is how the quantum teleportation logic actually works. How actually we can transfer some quantum state without transferring it, meaning we can actually reconstruct it at the receiver end as well. Okay, so initially sender has something like Alice has something which is alpha 0 plus beta 1, but at the end of the time evolution of the entire quantum operation, it is like Bob who has the state alpha 0 plus beta 1. Anything else? Anything else? Anything else doubt you have? So remember, in short, this is basically a theorem where we convert it from classical to quantum, kind of. Where we mention like maintain a like dictionary where whatever classical information is given to us, we take it, we forward it through some classical channel, maybe a telephone, maybe an SMS, and from that information, the quantum information can be restored. So no doubt till this part. Please let me know right itself. Okay. Then, yeah, okay. So I hope this is clear. So what we covered is we covered the Bell state entanglement, follow and how to actually realize that with the help of the Hadamard and Synod gate. Then we have seen one of the like features of quantum mechanics, which is the quantum teleportation. The next theory that we will enter into is the reverse theory, which is the dense coding or super dense coding, where we actually will be sending the quantum information in order to get back something in the classical setting. So, in order to derive what is the classical information that Alice wanted to send to Bob in super dense coding, we will be utilizing some of the quantum state. And then, so initially we will be starting with some quantum state, then we will be doing some quantum evolution or time evolution of that quantum state based on the time evolution or how the quantum state behaves. At the very end, we will be able to understand that what are all the quantum like operations that had taken place. From that we can understand that what are the classical information that is behind the quantum state evolution. So here from the quantum state evolution we will try to map what is the classical information we want to extract. Okay, now I want to give a 2 minutes break. Post that we will start. So let me take a 2 minute break. So it's like a 3:57, so around 4 or 3:59 we will be starting. I hope that is fine. So just take a small break, then we will come back.
Okay, ma'am.
Yes, sure. Yes, let us start. Uh, so, mm, so the next theory is where we will be starting with the reverse of the teleportation process, which is known as the dense coding, or super dense coding. Okay, and also remember, like through the like teleportation and super dense coding, we're also kind of implementing or understanding how a quantum circuit works. So if you're noticing that as well, right? So with this thing, I think that concept will be even more clearer. So here the idea is that Alice wants to send. So in teleportation, Alice wanted to send some quantum state to Bob. Now here Alice wants to send 2 bits of classical information. 2 bits of classical information. They are 0001, 10, and 11. And in order to send this thing, Alice will be using or utilizing. So an Alice will use a quantum state to send this classical information. So another point is Alice will be sending 1 bit of quantum information through what? Through, definitely, if it is a quantum information, then that means through a quantum channel. So through some quantum channel, and Bob should be able to extract. Bob will extract 2 bits of classical information. So it's from 1 bit of quantum information to 2 bits of classical information. And hence it is called dense coding or super dense coding. Okay, so here also, so we can understand now that it is exactly the inverse process of teleportation. And here also we have used an entangled state to achieve this. So the starting point will be, so let me just mark it like a generic idea. So the generic idea here is point number one. So we will start with an entangled Bell state, which is again 00 plus 1 by root 2 kind of thing. We'll be starting with that. Second is, out of the Bell state, one will be with Alice. So Alice has 1 qubit, and Bob another qubit of Bell state. They will share 1 qubit each. Then point number three is, Alice will send, or say Alice will, first Alice will do certain operation on her part of qubit. That is some of the quantum operations or quantum oracle that Alice will be operating on her part of qubit. Fourth is, then after these operations, Alice will be sending the modified qubit to Bob through some quantum channel, right? So now is the state where Bob has a modified quantum state. Who has done the modification? Alice has done certain modification. And what is along with that common available to Bob? That is like one half of the entangled pair is already available to Bob. And also Alice has said through the quantum channel a little bit of a distorted or some operated quantum state. Now, step number 5 is Bob, on receiving the modified qubit, on receiving the modified qubit from Alice, of course, and along with the original part, that original part of the qubit that Bob already has. So now Bob has two information. First is what originally Bob had, which is a part of the entangled bill pair. Second is what modified qubit Bob has received from Alice. On both the things, he will do certain measurements and based on that, he will infer what two classical bits of information Alice wanted to send to Bob. So the algorithm is pretty easy. Initially, we will be starting with some entangled pair creation for the Alice and Bob both, where both of them will be sharing one qubit each. Next step is Alice will be choosing some quantum state that he wants to transfer to Bob. And but after that, Alice will be doing a certain operations or certain modifications on her part of qubit and then send the modified qubit to Bob. So Bob initially has something from configuration angle that is one of the qubits of the entangled pair. Right now, Bob has received some input from Alice in terms of a modified quantum state. Once Bob has both the information, what Bob will do, he will do some measurement on his part of qubit, and based on the measurement outcome, he will try to infer that what are the two original bits of classical information that Alice wanted to send to Bob, right? Now, on that note, the schematics of the dense coding circuit will be circuit. So this will look something like this. So this is 0, then it's Hadamard, another 0, and this is the control knot, and this is the Bell state creation. By now you should be knowing, you have seen this sub circuit already. So this is the Bell state generation. After that, there is a unitary transformation. on Alice's part of qubit. So this is some unitary operation that Alice wants to perform. Then this will come here because this is a quantum input. So this is a quantum channel followed by an Hadamard. This is just before measurement. So this entire thing is a part of Bell state measurement. So that means here during the generation step it started with 0 product 0, then we are applied an Hadamard, so it is 0 plus 1 by root 2 product 0. So it is basically 0 0 plus 1 0 by root 2. So that on C naught will become 0 0 plus 1 1 by root over of 2. So the entangled state, so the entangled state that Alice and Bob both share is 0 0 plus 1 1 by root over of 2. Now say Alice wants to transfer just a minute. Yes. So now say Alice wants to transfer either 0 0 or 0 1 or 1 0 or 1 1 to Bob. So this is what Alice's ask is, or the ask of the supertext coding is. Right? Now remember that what Alice wants to send is 0 0 0 1 1 0 and 1 1. And depending on what Alice wants to send, so depending on Alice's requirement, Alice will do certain operations on the entangled Bell state. But this is something that Alice is doing only on her part of qubit. Right? Say, for example, this is very important. Only on her part of qubit, not on the entire entangled state. Now say Alice wants to send 0 0. Then Alice will do nothing. Again, this is a dictionary rule. That means 0 0 plus 0 1 is something that is received by Bob. Now, how Bob will interpret this thing, that is a separate story. But initially, right now, if Alice wants to send 0 0 to Bob, then Alice will not do any quantum evolution or quantum operation on the entangled Bell state on her part of qubit. If it is like 0 1, then what Alice does is Alice will do an X tensor product I. So this X is On her qubit, that is Alice's qubit, X is applied. X is a NOT gate or the Pauli X matrix. And on this is on Bob's qubit, identity, that is nothing, is applied. So therefore, this will look like this. So initially it's 0, 1 and 1, 1. So that means only I have to apply X on Alice's part of qubit. That means these two are Alice's part of qubit. So that means it will be 1, 0 plus 0, 1 by root over of 2. Okay. Now, next is if Alice wants to send 1, 0, then the operation is Y product I. Now let us calculate what is this thing. So sigma Y is basically 0 minus I 0. This is the Pauli Y matrix, right? So because of this I, we will introduce another I over here. So it's IY product I. So that means what will be I into sigma Y? That matrix will be I into 0, 0. This is minus I into I. That is minus I square. I square is minus 1. So this is plus 1. This is similarly minus 1 and this is 0. Now, if we apply this I sigma Y on ket 0, then it will be 0, 1 minus 1, 0 times ket 1, 0, which is nothing but 0 minus 1, that is minus 1. And similarly, I sigma Y1 will be 0, 1 minus 1, 0 times 0, 1. So this is 0 into 0 plus 1 into 1, that is 1. And this is minus 1 into 0, that is 0. Into 0 into 1, that is 0. So this is your last ket 0. Okay. So these are the two operations. Now we will look into what will affect, what will happen if 1, 0 is applied. Or what was that state? So this will be applied on ket 0, 0 plus ket 1, 1 by root on application of 1, 0 by Alice. So that means this will become nothing but minus 1, 0 because Alice is part of qubit, Alice is part of qubit. So 0 will now become minus 1. So it's minus 1, 0. And 1 will become only 0. So this is plus 0, 1 by root. I hope it is clear. Okay. Now the next is if Alice wants to send 1, 1, then the operation is Z product I. So initially it was 0, 0 plus 1, 1 by root 2. And we know that on application of Z product I, it will be on first qubit, this qubit. So this will be 0, will be 0. And 1 will be minus 1. Okay. So likewise, there are 4 cases. This is case number 1. This particular thing is case number 2. And this is your case number 3. And this one is case number 4. Now, Bob has 4 different Bain states. Right? Now, Bob will use the C naught operator first. From where we are getting that? See, Bob will be using one C naught operator first. So Bob will one use a C naught operator first. Now, what will happen on the effect of C naught? We'll analyze that. Say the effect of Bob's C naught. Say 0, 0. If Alice wanted to send 0, 0, then Alice actually have sent this particular thing to Bob. Bob on that will apply Bob's C naught and it will become 0, 0 plus 1, 0 by root. Remember here we applied C naught on Bob's part of qubit. Okay. Now if 0, 1 is the information, then it is Alice must have sent this thing. That means that means Bob will do it and get it like 1, 1 plus 0, 1 by root. Similarly, for 1, 0, it will be minus 1, 0 plus 0, 1 by root 2. So on Bob C naught, it will be minus 1, 1 plus 0, 1 by root 2. Similarly, for 1, 1, it was initially this thing. And this will become 0, 0 minus 1, 0 by root 2. Now, if you observe carefully, this second qubit is 0 here, like this qubit and this qubit. So the second qubit is 0. And when else the second qubit is 0? It is here. And in remaining two cases, the second qubit is 1. Okay. Now, if we check in case number 1 and 4, where the second qubits are 0, so you have noticed that the second qubit is 0, and similarly in cases like 2 and 3, then the second qubit is 1. But if the second qubit is 0, then Alice must have sent either 0, 0 or 1, 1. 0, 0 was the first case, and 1, 1 is the last case. So that means if your second qubit is 0, Alice must have sent either 0, 0 or 0, sorry, or 1. And if the second qubit is 1, Alice must have sent either 0, 1 or 1, 0. Okay. Now since either the second qubit is 0, assuming that, then the first qubit can be or okay, considering the second qubit is 0 itself. Now this will be on Hadamard, and this also from Hadamard. It will look like kit 0, product kit 0, or it can be kit 1, or it can be this is 1, 1 source. So this is either 0 0 or it is 1 0. So there should have been a combination of logic, that is combination of measurement of the first and second qubit will enable that what are the classical bits of information that Alice wanted to send or Bob should be infer, right? So that means there should have been, pardon me, so there should have been a combination of logic, that is combination of measurement of the first and the second qubit. So this is with respect to the first and second qubit to enable what Bob should infer. Okay, so the logic is that can be interpreted from this. Say I have a second qubit and I have first qubit. And it can be 0 0, 0 1, followed by 1 0 and 1 1. Then the logic is with respect to the second qubit, and if you notice carefully, second qubit is 0, has the cases 0 0 or 1 1. Similarly, second qubit has 0, this one also. Second qubit, if it is 1, then it has to be this. Second qubit 1 has to be this. So this, or what are the remaining things? 0 1 1 0. What are the remaining things? This is like 1 0 followed by 1 1 0, sorry, 1 0 followed by 1 1, sorry. This is 0 0 and this is 0 1. So if the first qubit is 0, considering that it can be 0 0 0, similarly it can be 1 0 1 1. So it can be, this is 0, so it is 0 0 or 0 1, and here it is 1 0 or 1 1. What is the common point here? That is the result. It present in both of them, first and second qubit logic. So this is 0 0. This one is 1 1 is common. Here basically uh, 0 1 is common, and here basically 1 0 is common. So these are all the classical bit of information that Alice is supposed to get. Sorry, Bob is supposed to get. So this is the classical bits of desired information at output. Okay. Now exactly the way we have done with the like a first and like the two qubit entangled Bell state, we can also consider of having some advanced logic if we want to send some more information with respect to the three qubit Bell state as well. So how will that look like is this is something like this. So this is 1 by root 2 8000 plus 111 whole divided by root over of 2. This is known as gigahertz state. So with 3 qubit, you should have maximum implement if you have something like this. Everything is initialized with 0. If this is the case, then what is the superposed state? How it looks like? That is 1 by root over of 8 times get 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. This is the natural thing. But here we have, this is also like 3 qubit. Here also like 3 qubit, 1, 2, 3, 1, 2, 3, and 1, 2, 3. So all are 3 qubit. But here the amplitude is not 1 by root 8, it is 1 by root 2, and there are only two states. So how to do that? Say you are initializing all with 0 as you have done here, but only on the first gate, a qubit, you have applied one Hadamard. And then these qubits, you just have applied a simple C naught, as well as not from here, say here, from this. Okay. Yes. Now let us assume how it looks like. So initially it is all 0, 0, 0. Then I've applied Hadamard on the first qubit. So that means it will become 0 plus 1, 1 by root 2, let me take outside, times 0 and 0. So it's 1 by root 2, it's 0, 0, 0, plus 1, 0, 0. Okay. So this is on Hadamard. Now what we are applying? We are applying two C naught gates. So this is your Q0 basically. This is Q1. This is Q2. Let me also mark it over here. This is Q0. This is Q1. This is Q2. Similarly, this is here Q0. This is Q1. This is Q2. So 1 by root 2, 0, 0, 0 plus 1, 0, 0 on C naught Q0, Q1 will look like this is Q0, this is Q1. So this will look like 0, 0, 0 will be as it is, plus this is 110. Okay. Now if we apply another CNOT gate, which is Q1 to Q2 as per the circuit, then it will be, now this is your Q1 and this is Q2. This is Q1 and this is Q2, where Q1 is the control and Q2 is the target. So this thing will be as it is plus 1, 1, 1. Because the control is 1, so this target will also become 1. So with these two operations only, before Hadala, after Hadamard, we actually have gone into the gigahertz states. So all these things are entangled pairs that are used depending on the application. Okay. Anywhere you have any doubt, let me take a pause here. Anyone who has any doubt, you can ask. Right now, let me know if you have further confusion on Bob's side. Bob is just receiving something. See what Bob is receiving. Bob is receiving some modified qubit from Alice's end. After that, based on what are the modifications, Bob is doing a certain operation on his end. Depending on the operation outcome, then he is analyzing. Now he has his set of like qubit as well as whatever he has received from Bob. So he's analyzing both of them, having a dictionary. He's referring to that dictionary, and in that graph, yes. So in that graph, whichever you have common, that has to be like, now Bob is taking first is what is the content of the second qubit. Then Bob is looking that okay, if the second qubit is 0, then my logic says that it can be 0, 0 or 1, 1. Only these two. Now since Bob has applied some measurement on first qubit as well, so he has got that if I'm getting a resultant state as 0 in the first qubit, then I must be having 0001 status in the first qubit. Now he is putting both the logics in an intersecting manner. Now second qubit 0 means it can be either 0, 0 or 1, 1. First qubit 0 means it can be either 0, 0 or 0, 1. So what is common? Like 0, 0. So from that, Bob is interpreting that definitely like Alice must be trying to send the result 0, 0 to Bob. Sigma y is complex because that is in that xy plane of the uh, like analysis or the Hilbert space. So that is why this, because everything is in the complex plane, right? So sigma y is something that enters into that plane where we have to introduce that I coordinate, I conjugate kind of thing into picture. That is why I mentioned that we generally need that sigma x and sigma z, and mostly sigma z is the most important one as we need it for the purpose of measurement. But sigma y is also something that we need in the xy plane. That is why, since we are getting in the I mode of like as the matrix element, that is why we are incorporating a separate I as a scalar multiple with the Pauli y. If Q0 also gives you the same thing, then you can do that, no issue. I guess Q0 also, yeah, you can do that as well. No issue. You ultimately need to implement 000 plus 111, which is a gigahertz state. Now, what you have to put for as a control, that depends on you. You can do that, no issue. Anything else? Broadly, conceptually, is there any gap that you have got? In, again, I'm doing a recap. In no cloning, as well as teleportation, as well as like super dense coding, as well as whatever we covered in the interference, like increasing and decreasing of quantum states and all. Is there any doubt? Just let me know that, please. My voice is very much broken. So again, it's kind of a viral I was having, so it's coming back again and going and coming like this. Instead of Hadamard gate, can we use any other gates? For what? For the purpose of superposition? If that is your question, then the answer is no. There is only one gate that you can use for superposition purpose, that is only Hadamard. All the remaining gates are for separate uses, but no one guarantees superposition. Okay. Okay. Uh, Thank you. And also, don't worry, the class is not over yet. I just want to show something. Let me just open it, then I will share the screen. So it's not here. So just give me some time. So I guess it is like, just give me some time. Yeah. Yes. Let me share. Uh, yes. So I think it's visible to you. So this is the like platform where you can play with the platform. You can do anything. So all these are. This is just like 2 minutes I want to spend on this, as this is out of the scope of like QT02. But definitely, I think in QT03 and 4, you will be having a lot of detailed understanding of these things. So let me remove it. So you can actually remove it from this, and you can remove this Hadamard as well from this. So what is the interpretation of this is C4 is the classical measurement. Since you have like 4 registers, so that means 4 bits of outcome you are going to receive. That is why it's C4. And also like Q0, Q1, Q2, Q3, these are the 4 qubits, right? And what you can see in this panel, so you can have this access if you just click on quantum.cloud.ibm.com. Okay, that is the thing. Let me write it down. So it's quantum dot cloud dot ibm dot com. So you can directly access the kind of the composer that they have, and this kind of window will open. You don't have to create also anything like that. So the thing is, what you can observe here is this is a q sphere. Q sphere is something which they actually have defined for their purposes. Okay, this is the table view where the computational basis states as well as the probabilities, you can see it over here. So since I've done nothing, so initially it's like, and since 4 registered, like 4 qubit registers have been initialized. So if nothing is done, it is like initializing it with 0000. That is why in 0000 you are getting 100% probability. Let me go back to the graph view. And in the bottom also you can see the probability density curve. This is the PDF function that you can see, or the probability density function. While you interpret it, you just read it like this: 0, 0, 0, 0, 0, 0, 0, 0, 1. Let me do a little operation. Let me create that entangled Bayes state, or how you can do that. So what was it? We need first, what is we require? So we all require the kind of, let me clear this thing. Let me clear this one as well. So we have right now two qubits, Q0 and Q1. So you can see, and what output we want to get out of the entanglement? It's a 0, 0 plus 1, 1. So that means first you have to apply. So it's a drag and drop kind of thing. So just drag and Hadamard gate over here. If you only apply this thing, you are going to get 0, 0 plus 0, 1. Now you understand why it is? I hope so. Just consider the, like, LSB is the first qubit here. Okay. LSB is the first qubit. MSB, or the second part of the decimal part, is the second qubit. Unlike the way we do here. So it's kind of that inverse mode. So the since I've applied on Q0, Q1, so Q0 on Q0, I've applied on Hadamard, so it has made it like 0 plus 1. That is why in 0, 0 and 0, 1, so Q1 0, that 0 is simply getting appended with the Q0 content. So if it is 0, it is becoming 0, 0, because Q1 is 0 and Q0 is 0. If Q1 is 1 and Q0's, if Q0 is 1 and Q1's 0 is being appended, then it is creating 0, 1. That is it. Now, what is the next thing? We have to apply the synod gate. What is the synod gate? This is the synod gate. You can see this is a NOT gate. This is the synod gate. So this is a simple synod gate. Just put it over here. And you got your first entangled build state. What it is, like 0, 0 plus 1, 1. And also check for the probability. It is 50-50%. Right? Now, let me consider a little change over here. Let me delete it. And let me also delete this Hadamard. Let me put first a NOT gate over here. Right? That means Q0 is right now 0 itself, as you can see in the MSB. But Q0, which was initially 0, that is why we got a high on 0, 0. Right now we are getting a high on, say, 0, 1, or alternatively 1, 0, considering Q0 is 1. So that's why you are getting 100% probability with this. Now if I apply the similar thing over here, say I had a mod followed by a C naught. So what you are going to get, you are again going to, here also you're going to get a 0, 0 and 1. Now how to verify that? Just verify it through the mathematics or the matrix. And also notice one thing, that is here in OpenQASM, that is a quantum assembly version 2. Okay, this is the assembly part of it. Here your entire quantum programming language will be automatically generated. You don't need to do anything. So X is the NOT gate. So its symbol is like, or the instruction is like XQ0, then Hadamard on Q0, then CX, which is controlled NOT. That is why CX, control NOT on Q0, Q1, where Q0 is the control, Q1 is the target. Right? Now, if you take anything arbitrarily, okay, you can see that dynamically you can have a difference. There is a visible difference you can notice in the contents of this thing as well. See here. Likewise, dynamically you can notice that the code will be automatically generated. From the code you will be understanding that what is the logic. So it's a two-way mapping, either from the code to the circuit or the circuit to the code. And these are the quantum gates that you can see, that those are available with Qiskit. And by playing with these gates, by simply dragging and dropping them and just looking into the probability densities, how they are changing, you can actually have a flavor of how the quantum computing or the programming languages work as well. Also, I want to just mention one more thing, that is, there is a Qiskit version of it as well, where you can look into it. from the Python perspective as well. So this is the entire part. So any form that you want, you can have this thing. And also, right now we are in the era of ChatGPT. If you want something in other languages like the PyQuil or some or say some Google Sark or this IBM Qiskit or some other language, then if you just simply put one code, then that transpiler service is automatically available. And before that, you can write it from the ChatGPT, and then you can verify or validate that code as well. But automatically, what I want to say is you have to understand that how it works. What are the interpretation of everything? Okay, that is the most primary thing. Writing the code only does not matter for quantum because everything is available, both the Python version as well as the assembly version. So initially, when you are starting, you can have a look on that and try to understand that. Once you have a good understanding, try to solve it mathematically. Once you have solved it, once you arrived at certain kind of a after measurement, what is the outcome and all, have the detailed mathematics understanding, you just come here, come to this platform, verify whatever circuits you are getting, and try to analyze that what is the outcome you are getting mathematically and whether that is matching with the outcome that it is showing to you. Okay, so this is all I wanted to show. uh, I hope it is clear. Have you at least got that platform? See, I'm pretty sure uh, the Qiskit Python version. Just go to the Qiskit documentation. Everything, every details you will be finding over there. How you can create your own like a Qiskit account, then how you can proceed with it. And for what I have just have shown to you, you don't have to do anything. You directly link on that particular um, hyperlink, and directly you can have that kind of feeling. So what we covered, at least for that understanding, you can directly go to that. You can play with the interference. You can check that what are the how interference is getting affected with respect to the quantum state reduction and all. Okay. So how to know logically it is correct? In order to know that, first of all, you have to rely on IBM that they are providing it correct. Second is you can also verify it mathematically from any arbitrary example. Let me just show you one example at least so that you have a better understanding on how you can validate it. Say, let me take as example. I just have shown you one example like Hadamard and Synod forms that one. So let me arbitrarily take something. So say this is X, this is H, and this is X. Then this is your C naught. This is your C naught. And so this is a control node. Let me have this much. Let me understand what do I mean by this. So initially, once you have this thing in a quantum circuit form, this is the quantum circuit form. So what in open chasm, or say simply the quantum computing language, which was the very primitive, the first primitive language, programming language for quantum, how to interpret it. So this is your Q0. So first you are applying a X of Q0. This is the first instruction. Second is you are applying an Hadamard on Q1. Third is you are applying an X on Q2. Fourth one is you are applying a C naught, where Q0 is the control and Q1 is the target. Fifth is where's another C naught where Q2 is the control and Q0 is the target. 6 is it's a C square naught or CC naught where Q0, Q1 is the target and Q2 is the control. Q0, Q1 is the control and Q2 is the target. Okay. Now, so it's XHX, this thing. Let me just again, please write it. So it's XHX This is this thing, I guess. Yeah. And then this one is this thing. Yeah. So initially it's 0, 0, 0, no change. So we have started with 0, product 0. This is how you can validate any of the output that you are getting in quantum. So first is you have to apply a NOT gate. So on the first and third qubit, you have to apply a NOT gate. And on this, you have to apply a Hadamard gate. So Hadamard will make it this thing. And 0 or NOT will become 1. And this also will become 1. Right? So this is nothing but 1 by root 2. You take it as common. So this will be 1, 0. Let me just 1, 0 plus 1, 1. Product 1. So this will be 1 by root 2. If I write it down, it's 101 plus 1, 1. So till this part, this is the story. Okay. Now, what we are doing is the first C naught, like C naught, Q0, Q1. So this will make it. Now this is Q0, this is Q1, Q2. Once you understand that this is how you can interpret of the any of the outcome or algebraic expression in a quantum, it is actually very easier for you to get that what is going to be the final output. Once you understand it, then only you can enter into quantum algorithm to understand that how this particular outcome can be derived. So what are all the logics, what are all the quantum gates that you have to apply in order to get this desired outcome? For that, first you have to understand that how to interpret the outcome, right? So if you do that, see Q0 and Q1. So that means it will be 111, and this part will be 10. First synod is done. Second synod is what? Synod Q2, Q0. Now Q2 is the control and Q1 is the target. That means it will be 1 by root 2, 011 plus 00. On this, now we have to apply C square naught Q0, Q1 and Q2. That means these two are 1. In both the cases, nowhere both the variables are 1, so there will be, that means no change. So it's 011 plus 00. So this is the final outcome. Output. That means in your probability density function for the 3 qubits, what are all the variables? 000, 001, 010, 011, 100, 101, 110, 111. So 011, this thing, and 001, this thing will be high. And what will be their probability? 50%. Why? Because 1 by root 2 is the amplitude and the probabilities are half. So only you can get a high over here and a high over here. And any manipulation on this state will be directly having that reflection in the probability density curve. Clear? So this is all that we wanted to discuss. Unfortunately, quantum error correction we cannot do here, but I think you will be having that exposure very soon, or maybe I also might be asked to cover that in some later part. So definitely we'll be having that exposure. Okay. So now you know that how to correct it logically, how to check that whether that is correct. Anytime remember quantum computing is 90% mathematics and which is a part of the linear algebra and matrices. Everything is in form of matrix. Once you understand the matrix format of it, you know that what does what, you will be having a detailed understanding of the algorithm or the logic as well. Maybe not in first term, but maybe in second, third, fourth, fifth turn, but definitely we'll be having a detailed understanding. Because it's absolutely logical. There is nothing mythology, like nothing kind of a mysterious kind of happening over here. It is even more logical than the classical ones because every operation here are reversible in nature. Think it is clear you enjoyed the first 5 days in QT02. And yes, so we have Navratri, we all have Navratri meanwhile. So just to enjoy it a lot. And maybe on 6th onwards there will be having, like I will be having some more classes on complexity and all, so we will be having a lot of fun over there, where primarily we will cover the classical computational complexity classes. We will understand the loopholes, we'll understand why the like traveling salesman problem in very detailed fashion. All the detailed logic of NP-hard problems will be clear by that time. The decidability, the reducibility, all the formal formulation of complexity theories and performance of a algorithm, that will be cleared as well. Once we have done that, we will then see the quantum complexity classes. I think this will be starting from 6th of October, if I'm not wrong. Meanwhile, just enjoy your class, just do a recap and have a good exam. I shared the questions already. I think it will be fun for you as well. Yes, sir. Up to you.
Thank you, ma'am. Thank you for this 5 engaging days. I think the students actually enjoyed these lectures, which can be easily observed from these interactions that they're having. I mean, you have made the learning so enjoyable that also we are discussing over here and we also try to understand the things. And obviously, the participants had a very good questions throughout the sessions. Thank you, ma'am, for that. And also, Dr. Pilli is not here today. He is traveling somewhere. So he also asked me to convey his gratitude towards these sessions. And thank you, ma'am, for that.
Yes.
And also, we'd like to thank you on behalf of the EICT Academy and APSCHE for attending or making our session so interactive and delightful. And we'll also see you. We'll have chance to interact with you in the other courses that is also starting soon. And thank you once again, ma'am. So if you have some final conclusions, remarks
Thank you. One
with
thing
the
is, I was throughout the like every day in all the 5 sessions, I was so motivated by the questions asked. It clearly reflects that they're listening, they're engaging into the conversation, they're asking questions, they're trying to understand. A few of the like participants, they already have certain like previous knowledge, they're trying to validate that as well. So it is very good, very good. I had a great time for like having this kind of an audience. This is great, great feeling altogether.
thank you, ma'am. Yeah, we are also feeling the same. So thank you once again, ma'am. And you also have a great Navaratra ahead. So you'll be in West Bengal, you're in Delhi.
I am in Kolkata right now.
So you had a cloudburst, no? We have been listening to the news for the last few days.
Yes,
Yesterday
yes,
also.
yes, yes. And also, like, we are all like my entire family, we are having the viral fever. The weather and all that
Oh,
is very bad in Kolkata.
yes, ma'am.
Yeah.
I mean, I'm also from near the place, so I normally travel there in winter only because of the dry season.
Yes, yes. I was in Noida, but last for 1 year for some family issues and all, I'm staying in Kolkata
Oh, okay, ma'am.
because I have a
So thank you, ma'am.
permanently work from home like thing.
Okay.
That is why,
That's good.
yes. I am into quantum teaching, or I'm in teaching for a lot many years, honestly. But in quantum with ENICT, I am associated uh, since 2021 for
And
quantum.
you also work in blockchain, right, ma'am?
Little, not much, but like because
Oh,
in quantum cryptography, while I was doing that one, there we had an intersection kind of thing. So I worked on that blockchain.
great, ma'am. Great. Nice talking to you, and all.
In
I
PwC
hope
right
that.
now, I'm doing Gen AI and all. I honestly I'm not getting that flavor of working or getting that exposure because every time industry, that they're like shifting from one technology to another technology, depending on the funds and all.
Right.
So I'm
Right.
not getting that feeling to work on quantum, but I'm doing PhD and all these things on.
So basically, there you work as per the requirement of the company, not what you choose
Yeah, I
for
like
your
teaching.
life.
I like quantum. And Dr.
Right,
Pilli, he knows it very well. Like these are two things that I love very much.
right. I hope
Yes.
that you will soon come back to teaching once again because your students
I'm
will
really
really
trying.
love.
Honestly, I'm trying. Honestly, I'm trying. In a public forum, I'm telling that
All
I'm trying. Yeah.
all the best, ma'am. Right.
Thank you.
In
Thank you
fact,
so much.
we'll be happy to have you with us.
Thank you.
Thank you,
Definitely.
ma'am.
Thank you, sir.
Thank
Thank
you
you.
once again, ma'am. And it was a great time, all these 5 days. Right, ma'am.
Yeah.
So thank
Thank you.
you. And also participants, thank you for being with us. I hope you also enjoyed this 5 days. And by the way, ma'am, it's almost over. We have some discussion with the students. If you want, you can leave. And as for
Okay.
the other things, the committee will discuss with you, ma'am. We'll get back to you, ma'am.
Sure, sure, sure. And I will share the
Thank you.
content just yeah within 5 minutes. Yeah.
Right.
Okay. Thank you. Thank you.
Uh, Thank you, ma'am. And the participants, from tomorrow, the sixth session will have another module. You have probably already seen. Dr. Ashraf Babu will be with us from tomorrow for the next 4 sessions. Then we'll have this the syrup breaks, and then afterwards we'll have another course from another schedule from Ashraf Babu and so on and so forth. By the way, another point is from Friday we'll have this quiz. Friday evening at 6 o'clock we'll launch the quiz, and it will be of 20 questions, and you will have to complete that by the Sunday. So what you can do is you can refresh all these 5 lectures. It's already there in the public domain. The slides are almost, the 4 slides are already loaded in the canvas. The fifth one will also be loaded very soon. So you can go refresh your things, then you can go because it will be given only 30 minutes to attempt all the 20 questions. So yeah, please study and then come back to the questions, but you have to finish by Sunday evening. After that, there will be no extension. So yeah, thank you all, and we'll see you tomorrow at 3 p.m. So please be there due time. We'll have another session on statistical physics, which will be relevant to this. So yeah, so we'll see you tomorrow at 3 o'clock.